Right now, as you click on this video, our planet is drifting through a region of space that is measurably emptier than it should be. Not slightly emptier, not within the margin of error. Roughly 20% less matter than the surrounding universe, extending in every direction we look for nearly 1 billion light-years before the density climbs back to normal. The bubble we are sitting inside is approximately 2 billion light-years across. It has a name. Astronomers call it the KBC Void, after the 3 researchers who confirmed it in 2013 by mapping the positions of 35,000 galaxies. And its existence may quietly be rewriting one of the most important numbers in physics. To understand why this matters, you have to start with a simple fact about cosmology. The universe is not arranged like a uniform fog of galaxies. It has structure. Galaxies cluster into groups, groups into superclusters, superclusters into immense filaments that stretch across hundreds of millions of light-years. Between those filaments are voids, vast regions where matter is sparse. This pattern, often called the cosmic web, is expected. Our standard models predict it. What they do not predict is a void on the scale of the one we appear to be living in. The astronomers who found it, Ryan Keenan, Amy Barger, and Lennox Cowie, were not searching for an anomaly. They were doing something more routine. They were comparing the number of galaxies in our local volume of the universe to the number that theoretical models said should be there. Their counts were systematically low, not in one direction, not in some patch of sky that could be blamed on dust or instrument error, but uniformly low across the entire sphere surrounding the Milky Way. They cross-checked their results against several independent surveys, approached the problem from different angles, and the answer kept returning the same value. We are inside an underdense region so large that it dwarfs every previously cataloged void. At first, that might sound like an interesting curiosity, the cosmic equivalent of noticing that your neighborhood happens to have fewer trees than the surrounding forest. But the KBC Void is not a small statistical wrinkle. It is enormous, deep, and in a very specific way. It appears to be biasing the most precise measurements modern cosmology can make. To see how, consider what is arguably the most important number in cosmology, the Hubble Constant. It describes how fast the universe is expanding. More precisely, it tells us how many kilometers per second a galaxy recedes from us for every megaparsec of distance between us, where 1 megaparsec is about 3.26 million light-years. There are 2 main ways to measure this number, and for the past decade they have stubbornly refused to agree. The first approach uses the cosmic microwave background, the faint thermal afterglow of the universe from when it was about 380,000 years old. By analyzing the detailed patterns in this ancient radiation and feeding them through cosmological models, scientists can calculate what the expansion rate must have been in the early universe and what it should be today. That method consistently returns a value of about 67 kilometers per second per megaparsec. The second approach builds a ladder of distance measurements using objects with known intrinsic brightness, particularly Type 1, a supernovae, and Cepheid variable stars. By comparing how bright these objects truly are with how bright they appear, astronomers calculate their distances. Combined with redshift measurements, this gives a direct estimate of how fast nearby galaxies are receding. That method consistently returns a value of about 73 kilometers per second per megaparsec. The 2 numbers do not match. The gap is about 9%, and both measurements have been refined and re-verified by multiple independent teams using different instruments. The discrepancy has reached what physicists call a 5 sigma level of significance, which is the formal threshold for claiming a discovery. The probability that the gap is the result of random error is less than 1 in a million. This disagreement has come to be called the Hubble Tension, and it is one of the most actively debated problems in physics today. Here is where the void becomes more than a curiosity. The local Hubble constant is measured using objects that are sitting inside the same underdense bubble we inhabit. The matter that is missing from the void's interior, that 20% deficit, is not gone. It has been pulled outward over billions of years and now sits in the denser filaments and walls surrounding the void. Those exterior concentrations of matter exert a gravitational pull on everything inside, including the supernovae that astronomers use as distance markers. Galaxies within the void are not just receding because space itself is expanding. they are also being tugged outward by the gravitational imbalance created by the void's geometry. This adds a small but systematic extra velocity to nearby galaxies. When astronomers measure their recession speed and convert it into an expansion rate, the number comes out inflated. The void is essentially giving every galaxy inside it an additional outward kick, mimicking a faster expansion than is actually occurring on cosmic scales. Detailed calculations show that a void with the KBC Void's measured size and depth, roughly 1 billion light-years in radius and about 20% underdense, can produce almost exactly the boost needed to explain the discrepancy between the two Hubble measurements. If this picture is correct, the implication is striking. Scientists did not make a mistake. The local measurement is accurate, but the location from which that measurement was taken introduces a built-in bias. We are not measuring the universe's true expansion rate. We are measuring the expansion rate as seen from inside a gravitational anomaly that amplifies the apparent value. To picture what this means physically, it helps to lay out where we actually are within the larger architecture of the cosmos. Our galaxy, the Milky Way, is one of about 80 galaxies bound together in what astronomers call the local group. That group spans a few million light-years and includes Andromeda, the Magellanic Clouds, and a swarm of smaller dwarf galaxies. The local group is itself a small piece of a much larger structure called the Laniakea Supercluster, identified in 2014 by tracking the velocity flows of galaxies across our region of the universe. Laniakea contains about 100,000 galaxies spread across 520 million light-years. Its name comes from Hawaiian and roughly translates to immeasurable heaven. The structure is defined not by simple proximity, but by gravitational flow. Every galaxy within Laniakea is being pulled toward a common center known as the Great Attractor. The Milky Way sits on the outer edge of Laniakea, gravitationally bound to it, and our peculiar motion, the part of our velocity not explained by cosmic expansion, is partly directed toward that Great Attractor. And here is where the scale of the KBC Void becomes hard to absorb. Even Laniakea, this enormous supercluster of 100,000 galaxies, fits entirely inside the void. The void is so vast that a structure of Laniakea's size barely registers as a perturbation within it. Our position is not at the void's exact center. Measurements suggest that the Milky Way is somewhere between 200 and 400 million light-years from the geometric middle. But the void extends about 1 billion light-years in every direction from that center, so we are well inside it, surrounded by underdense space in all directions. Beyond its edges lies a shell of higher density structure, filaments, and clusters where the cosmic average reasserts itself. When astronomers look outward, they see this shell as a concentration of galaxy clusters at a particular range of distances. It is, quite literally, the wall of the bubble we live in. There is also a smaller, distinct structure right next to us, called the local void, spanning about 200 million light-years. Our galaxy is actively flowing away from the local void at around 260 kilometers per second as part of a broader sheet of galaxies called the local sheet. Add up all of these effects: the pull toward the Great Attractor, the outflow from the local void, the gravitational influence of the Virgo cluster, about 60 million light-years away, and the future merger trajectory with Andromeda, and the Milky Way ends up moving at a total peculiar velocity of roughly 627 kilometers per second relative to the cosmic microwave background rest frame. That figure corresponds directly to a temperature dipole observed in the cosmic microwave background, and it is consistent with what you would expect for a galaxy sitting inside a large, underdense region. We are not stationary. We are being carried along by the gravitational landscape, and the void is a major reason why. To understand how a structure like this can exist at all, it helps to step back and think about how the cosmic web formed. By volume, voids are actually the dominant feature of the universe. Roughly 90% of the total volume of space is void. The filaments, walls, and clusters of galaxies we tend to focus on occupy only about 10% of the volume, but they contain the great majority of the mass. This distribution traces back to the earliest moments of cosmic history. During a brief period called cosmic inflation, occurring in a tiny fraction of the first second after the Big Bang, the universe expanded exponentially. Quantum fluctuations at subatomic scales were stretched to cosmic scales, imprinting tiny variations in density across the early universe. Some regions ended up slightly denser, by perhaps 1 part in 100,000, others slightly less dense. Those differences sound negligible, but gravity is patient and relentless. Denser regions pulled in more matter from their surroundings, becoming denser still. Less dense regions lost matter to their neighbors, growing emptier over time. Across hundreds of millions of years, this process built the architecture we observe today, a foamy network of filaments and sheets surrounding vast hollow regions. The voids themselves are not literally empty. They contain dark matter, just at lower concentrations, around 15% of the cosmic average density. They contain dark energy, which is uniformly distributed across all space and so present in voids at the same density as everywhere else. They also contain wisps of hydrogen gas and the occasional isolated galaxy. What they lack is the gravitational mass to build new structure. Without enough matter to seed clusters or filaments, voids stay voids and grow over time. This is where dark energy quietly takes over. In dense regions, gravity and dark energy compete. Gravity pulls matter together, while dark energy pushes space apart. The two partially cancel, and the expansion of dense regions is somewhat slower than the cosmic average. Inside voids, that competition barely exists. With so little matter, gravity contributes almost nothing. Dark energy dominates and voids expand faster than the surrounding universe. The faster a void expands, the emptier it becomes, which further reduces gravitational resistance and accelerates the process. Voids grow like bubbles, pushing outward and compressing the surrounding filaments into thinner, denser walls. This dynamic has a measurable signature. Galaxies near the edges of voids move outward faster than expansion alone would predict, and the velocity surplus matches what you would expect from the gravitational pull of denser matter on the void's exterior. The same physics applies to the KBC Void, and it is responsible for some of our galaxies' unusual motion. But the existence of the KBC Void becomes truly remarkable when you compare it to what theory predicts should exist. The standard cosmological model, often abbreviated as Lambda cold dark matter, has been extraordinarily successful. It accounts for the temperature patterns of the cosmic microwave background, the abundance of light elements forged in the Big Bang, and the general structure of the cosmic web. It also predicts a statistical distribution of void sizes. Small voids, tens of millions of light-years across, should be common because they form from the typical small fluctuations of the early universe. Medium voids should be less common. Extremely large deep voids should be very rare because they require unusually large initial underdensities that are statistically improbable given how smooth the early universe actually was. When researchers run computer simulations of structure formation using standard parameters and search for voids comparable to the KBC Void, roughly 2 billion light-years across, with a 20% density deficit, they find almost none. Some analyses estimate the probability of such a void existing in the observable universe at around 1 in 1,000. Other calculations are far more extreme, treating the KBC Void as something like a 10 sigma deviation from expected density. To put that in perspective, a 5 sigma result is already considered practically impossible by chance and is the standard threshold for claiming a discovery in physics. A 10 sigma result is incomprehensibly more improbable. And yet, here we are, sitting inside one. That creates an immediate logical tension. Either the standard cosmological model is missing something significant about how large structures form, or our galaxy happens to occupy an extraordinarily atypical position in the universe. Neither answer is comfortable. Critics of the standard model point to the KBC Void, along with other large structures like the Shapley Supercluster and the Sloan Great Wall, as evidence that the real cosmos generates more vigorous structure than simulations predict. Defenders argue that the universe is large enough to contain rare configurations, and that abandoning a successful framework based on one anomaly is premature, especially while the void's exact properties are still being refined. A third group suggests that the deficit may be closer to 10% than 20%, in which case the statistical pressure is reduced. Better galaxy surveys are needed to pin down the true value. The difficulty of fitting the KBC Void into standard cosmology has motivated some researchers to consider whether the underlying physics needs adjustment. One of the oldest alternative theories is modified Newtonian dynamics, often called MOND. Originally proposed to explain why galaxies rotate faster at their outer edges than standard gravity predicts without invoking dark matter, MOND modifies the law of gravity at very low accelerations. When applied to large-scale structure formation, MOND tends to produce more vigorous clustering, with denser clusters and deeper voids forming more naturally than under standard gravity. Simulations using MOND can generate voids of the KBC scale without requiring exotic initial conditions. The statistical improbability simply disappears. But MOND has its own difficulties. It struggles to explain gravitational lensing in galaxy clusters and does not reproduce the fine-scale temperature pattern of the cosmic microwave background as cleanly as the standard model. Some hybrid approaches blend MOND with small amounts of dark matter, such as massive neutrinos, to address these issues, though those models bring complications of their own. A broader class of modified gravity theories adjusts the behavior of gravity only at cosmological scales, leaving smaller scales untouched. Some of these theories effectively make gravity stronger inside low-density environments like voids, which would cause those regions to drain of matter faster and grow deeper than standard physics expects. Testing whether gravity behaves differently inside voids has become one of the more promising frontiers of observational cosmology. If you take a step back, all of these debates rest on a deeper assumption that has shaped cosmology for over a century: the cosmological principle. It states that on sufficiently large scales, the universe is homogeneous, the same everywhere, and isotropic, the same in all directions. No location is special, no direction is preferred. This is not just a philosophical preference. It is a mathematical convenience that makes the equations of general relativity tractable when applied to the entire cosmos. Without it, models become impossibly complex. With it, a few simple parameters describe the whole history and structure of the universe. The principle has been remarkably productive. It underpins the Big Bang model, the predictions of the cosmic microwave background, and the structure of modern cosmology. But the KBC Void puts pressure on it. A region 2 billion light-years across with a 20% density deviation is not a minor inhomogeneity. It is large enough to represent a meaningful fraction of the observable universe, and we appear to be near its center. The implication, one that scientists have spent 400 years trying to avoid, is that our location may not be typical. The history of astronomy has been a steady dethroning of Earth from any privileged position. Earth is not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of the universe. The cosmological principle was the final step in that progression, asserting that no location is central because all locations are equivalent. The KBC Void, if its measurements hold, suggests that while we may not be at the center of anything in a cosmic sense, we do happen to occupy a region that is statistically far from ordinary. Some cosmologists argue that the homogeneity requirement only kicks in at scales larger than the void itself, leaving the principle technically intact. Others invoke the anthropic principle to suggest that observers might preferentially form in mildly underdense regions where galaxy formation is favorable, so finding ourselves in a moderate void is not surprising. But these arguments are contested. A 20% deficit is not mild, and the size of the structure is not small. The debate matters, not just philosophically, but observationally. If the cosmological principle does not hold at the scale of the KBC Void, then every measurement made from our location, including every local determination of the Hubble Constant, is shaped by the unusual vantage point from which it was taken. We may be trying to infer universal properties from a position that does not sample the universe fairly. Before going further, it is worth pausing for a moment. If you find this kind of question interesting, the slow, careful work of mapping the cosmos and uncovering the ways in which our own perspective might be misleading us, consider liking this video and subscribing for more deep explorations of where modern science currently stands. There is much more to come on this topic, and it only gets stranger from here. Cosmic voids turn out to have unusual scientific value far beyond their challenge to the standard model. They are the best natural laboratories in the universe for studying dark energy. Dark energy itself was discovered in 1998 when observations of distant Type 1, a supernovae, revealed something unexpected. Astronomers had assumed that the expansion of the universe was slowing, that gravity was gradually pulling everything back together. Instead, the supernovae appeared fainter than they should have been, indicating they were farther away than a decelerating universe could place them. The expansion was speeding up. Some unknown energy component was pushing space apart, and it now accounts for about 68% of the total energy content of the universe. Unlike matter or radiation, dark energy does not dilute as the universe expands. Its density appears to remain constant even as space itself grows, which gives it an ever-increasing share of the cosmic budget over time. Despite its dominance, the nature of dark energy remains genuinely unknown. The simplest interpretation is that it is a cosmological constant, an intrinsic energy density of empty space, uniform across all places and unchanging across all times. Albert Einstein originally introduced this idea into his field equations and later treated it as one of his great mistakes. Modern observations have brought it back, now serving as the engine of cosmic acceleration. But it is not the only possibility. Dark energy could be a dynamic field, varying in strength over time or across different regions of space. If it was weaker in the past and stronger now, the history of expansion would have followed a different curve. If it varies across locations, structure formation would proceed differently in different environments. Distinguishing between a static and a dynamic dark energy requires precise measurements of how expansion has behaved at various cosmic epochs and in various cosmic neighborhoods. This is exactly where voids become indispensable. In dense regions, gravity and dark energy fight each other, and disentangling the dark energy signal from gravitational noise is genuinely difficult. In voids, matter is so scarce that gravity essentially drops out of the equation. Dark energy operates almost unimpeded, and the expansion of voids becomes nearly a direct measurement of its repulsive influence. By measuring how fast voids expand and comparing those rates to predictions from different dark energy models, scientists can constrain the underlying physics. If dark energy is a true cosmological constant, voids should expand at a rate that matches the standard model precisely. If dark energy evolves or varies, the rates will deviate. Void shapes provide a complementary test. Perfectly uniform dark energy would expand voids equally in all directions, keeping them roughly spherical. Any spatial structure or unknown forces could elongate or compress them along particular axes. Surveys so far show that most large voids are approximately spherical, consistent with uniform dark energy, but the precision is not yet sufficient to rule out modest variations. The KBC Void, being both the largest known nearby supervoid and the one we can study in the most detail, is particularly valuable. Its proximity allows astronomers to map its internal structure and velocity field at a resolution that is impossible for distant voids. As surveys improve, measurements of the KBC Void's expansion rate and shape will sharpen our constraints on dark energy far beyond what any other technique can currently achieve. The low-density environment inside a void does not just affect cosmology on the largest scales. It shapes the formation and evolution of the galaxies that develop within it. Galaxies inside voids grow up in relative isolation. Unlike galaxies in dense clusters, which frequently collide, merge, strip gas from each other, and feed material into each other's central black holes, void galaxies evolve with minimal external interference. Their lives are quieter, slower, and in some ways more predictable. This environmental difference produces distinctive characteristics. Void galaxies tend to be smaller and less massive than their counterparts in filaments and clusters. Many of them qualify as dwarf galaxies, barely massive enough to retain their gas against the outward pressure produced by their own star formation. Without the gravitational mass to anchor their gas, and without the encounters that fuel growth in denser environments, they remain modest in size for billions of years. In dense environments, mergers are one of the dominant drivers of galaxy evolution. When two galaxies collide and combine, the gravitational disruption compresses gas clouds and triggers intense bursts of star formation. Merger-driven activity is responsible for many of the most massive and luminous galaxies in rich clusters. It also feeds material into supermassive black holes, sometimes activating them as quasars, episodes of accretion so luminous that a single black hole can outshine the entire surrounding galaxy. In voids, this process is largely absent. Galaxies evolve according to their own internal dynamics, with star formation rates that are generally lower and growth that is gradual. They retain disk structures and spiral arms that would have been disrupted by repeated encounters in denser environments. There is, however, a curious twist. While most void galaxies are quiescent, a disproportionate fraction of them undergo brief, intense episodes of star formation called starbursts. This seems paradoxical at first. If void galaxies form fewer stars on average, why would they produce sudden bursts more often? The answer comes down to gas reservoirs. In dense environments, galaxies continuously lose gas through interactions with neighbors. Tidal forces strip material from their outer disks, and the hot diffuse gas that fills galaxy clusters can ram pressure strip gas out of any galaxy that falls in. Void galaxies escape these processes. They retain their neutral hydrogen for longer, building up large reservoirs of unprocessed gas. When something internal eventually triggers star formation, perhaps a small gravitational instability or the collapse of a particularly dense cloud, there is an abundance of fuel waiting. The result is a sudden, intense burst that consumes much of the reservoir before the galaxy settles back into quiet. This pattern of long, quiet periods punctuated by sharp bursts is distinctive. It contrasts with the more continuous, moderate star formation that characterizes typical galaxies in dense environments, and it reflects the unusual life history of galaxies that grow up in cosmic isolation. The chemical composition of void galaxies also differs from their cluster counterparts. Stars create heavy elements through nuclear fusion and disperse them into the surrounding gas when they die in supernovae. Later generations of stars form from this enriched gas, and a galaxy's overall metallicity, the abundance of elements heavier than helium, gradually rises over time. This process is slower in void galaxies because their star formation rates are lower. Void galaxies tend to have lower metallicities than their cluster counterparts, though the difference is smaller than naive models predict, suggesting that gas exchange with the surrounding intergalactic medium plays a meaningful role in chemical evolution. The dark matter halos surrounding void galaxies are also structurally distinct. Halos in dense environments are continuously perturbed by tidal forces from neighboring halos. They become elongated, compressed, and frequently misaligned with the visible galaxies they contain. Void galaxy halos experience far less of this disturbance. They remain more spherical and better aligned with the galaxies inside them. This simpler structure makes them easier to model, and they have become useful natural laboratories for testing predictions about how dark matter behaves on small scales. There is also a clear lower limit on what kind of galaxy can form inside a void at all. Below a certain halo mass, corresponding roughly to a circular velocity of 35 kilometers per second, the gravitational well is too shallow to efficiently retain gas through the cooling and collapse process needed for star formation. Halos below this threshold can exist inside voids, but they remain dark, harboring dark matter without producing visible stars. This explains why voids are not uniformly filled with countless tiny dwarf galaxies. At small enough scales, the environment is simply too empty for galaxies to assemble at all. The implications of the KBC Void extend beyond expansion measurements and into one of the most fundamental numbers in cosmology, the age of the universe. The current best estimate places that age at about 13.8 billion years. This figure comes from detailed modeling of the cosmic microwave background combined with the standard cosmological parameters, the matter density, the dark energy density, and the early universe expansion rate. If the local Hubble constant of 73 kilometers per second per megaparsec actually represented the true global expansion rate, rather than a value inflated by our position inside the void, the universe would have been expanding faster throughout its entire history. A faster expansion means it reached its current size in less time. Calculations show that this would imply a universe of about 12.7 billion years, roughly 8% younger than the standard estimate. This creates a concrete and uncomfortable problem. The oldest stars in globular clusters, dense spherical collections of hundreds of thousands of stars that formed together in the early universe, appear to be about 13 billion years old based on stellar evolution models. The dating method is reliable in principle. Stars of different masses burn through their nuclear fuel at different rates, and by identifying which stars in a cluster are just leaving the main sequence phase of their lives, astronomers can estimate when all the stars in that cluster formed. You cannot have stars that are older than the universe itself. A 12.7 billion-year-old universe with 13 billion-year-old stars is internally contradictory. White dwarf cooling times provide an independent age constraint that does not depend on stellar evolution models. White dwarfs, the remnant cores of dead stars, cool gradually and predictably as they radiate stored heat into space. The coolest white dwarfs we have observed have been cooling for approximately 12 to 13 billion years. This independently confirms a universe older than 12.7 billion years. The cleanest way out of this contradiction is to accept the void explanation for the local Hubble measurement. If the 73 value is inflated by our position inside the KBC void, then it does not represent the universe's true global expansion rate. The cosmic microwave background measurement of 67 kilometers per second per megaparsec applies to the early universe and to the global average, and the derived age of 13.8 billion years remains valid. The apparent disagreement between local and early universe measurements is not evidence that the universe is younger than we thought. It is evidence that our local neighborhood is unusual. This resolution preserves the age of the universe and removes the contradiction with stellar ages, but it requires accepting that nearly every precision measurement made locally over the past few decades has been systematically biased by our location inside an extraordinarily large, underdense region. That is not a small concession. It means our most refined measurements have been telling us about our neighborhood, not about the cosmos as a whole. Fortunately, the questions raised by the KBC void will not stay unanswered for long. A new generation of astronomical surveys is already underway or in preparation, designed with exactly the precision needed to settle these questions. The Euclid Space Telescope, launched in 2023 and beginning full science operations in 2024, will map the positions and shapes of billions of galaxies across a large fraction of the sky and out to distances of many billions of light years. Its primary scientific goals include measuring the expansion history of the universe and the growth rate of large-scale structure. These measurements will directly test whether dark energy behaves like a cosmological constant or like a dynamic field. Euclid will also identify and catalog thousands of voids at different distances and sizes, providing the statistical sample needed to determine how rare supervoids like the KBC void truly are. The Vera Rubin Observatory in Chile, when it reaches full operational capacity, will conduct a decade-long photometric survey known as the Legacy Survey of Space and Time. It will observe approximately 20 billion galaxies over the southern sky, mapping the three-dimensional distribution of matter to greater depth and completeness than any previous instrument. It will also discover supernovae at a rate of around 10,000 per year, dramatically improving the local Hubble Constant measurement. If the KBC void's influence on these measurements is real, the pattern should become unmistakable in Vera Rubin's data. The Dark Energy Spectroscopic Instrument, known as DESI, is already operating and is mapping galaxy spectra at a rate of millions per year. Its goal is to measure the Hubble Constant, the growth of structure, and the equation of state of dark energy through Baryon acoustic oscillation measurements, using the characteristic spacing of galaxy clustering as a cosmic ruler. DESI's results are expected to significantly tighten constraints on all of these parameters and to map the velocity field around the KBC void in unprecedented detail. The Square Kilometre Array, currently under construction in South Africa and Australia, will survey neutral hydrogen across the universe at radio wavelengths. Neutral hydrogen is the raw material of star formation and traces the distribution of matter in ways optical surveys cannot. It will map void interiors, characterize void galaxies across cosmic time, and measure how gas content evolves in low-density environments. It will also test the predictions of standard and modified gravity theories about how matter flows in and around voids. Together, these instruments represent an extraordinary leap in observational capability. The key measurements they will enable fall into several categories. They will constrain the Hubble tension by dramatically improving the precision of both local and early universe expansion rate measurements, determining whether the gap between them survives as systematic errors are eliminated. They will map the three-dimensional density field of our region with sufficient detail to confirm or revise current estimates of the KBC void's depth and extent. They will measure the statistical distribution of large voids across the observable universe, establishing whether the KBC Void is genuinely an outlier or whether standard cosmology has simply underestimated how common large underdensities are. If the new surveys confirm that the KBC Void is as large and as deep as current measurements suggest, and if comparable structures elsewhere are found to be exceedingly rare, the pressure on the standard cosmological model will intensify dramatically. Modified gravity theories and modifications to inflationary models will need to be taken more seriously. If instead the surveys reveal that large voids are more common than current simulations predict, it may indicate that structure formation in the real universe is slightly more vigorous than the standard model assumes, a more modest revision that preserves the overall framework while adjusting its parameters. Either outcome advances our understanding significantly. The void's existence has already forced cosmologists to examine assumptions that had been taken for granted, and the upcoming wave of data will determine whether those assumptions need to be abandoned or simply refined. The void we live inside is not a static feature. It is part of a dynamic structure that has been evolving since the universe began and will continue evolving as long as the universe exists. In the early universe, the cosmic web was just beginning to assemble. The first stars ignited in dense knots of hydrogen, about 100 to 200 million years after the Big Bang. The first galaxies took shape over the following hundreds of millions of years. The filaments connecting them and the voids separating them were smaller and less pronounced than today, with weaker density contrasts. Over the past 13 billion years, gravity has been working continuously. Dense regions have drawn in more and more matter, growing richer and more concentrated. Voids have lost matter to the surrounding filaments, growing emptier in turn. The cosmic web has become increasingly defined over time, with sharper density contrasts between voids and clusters. Dark energy adds a complicating factor to this evolution. For the first several billion years of cosmic history, matter dominated the energy budget, and gravity controlled how structures grew. But as the universe expanded, the density of matter, which thins out as space stretches, fell, while the density of dark energy remained approximately constant. About 5 billion years ago, dark energy became the dominant component, and since then, the accelerating expansion it drives has been competing with gravity. In this dark energy-dominated phase, the growth of structure has slowed. Voids continue to expand, but the rate of new cluster formation has decreased. Matter that was flowing toward filaments and clusters in the matter-dominated era is now being stretched apart by accelerating expansion before it can fully collapse. Looking forward, this process will continue. The Milky Way and Andromeda will collide and merge in roughly 4 billion years, forming a new combined galaxy. This merged structure will be the dominant object in the local group, but the local group itself will become increasingly isolated as accelerating expansion pushes other nearby groups beyond our cosmic horizon over tens of billions of years. As cosmic expansion accelerates, galaxies beyond a certain distance will recede faster than light can bridge the gap. They will effectively disappear from the observable universe. The local group will eventually find itself in an expanding void of its own, cosmically isolated even if not locally lonely. Over trillions of years, star formation will gradually cease as gas is consumed or expelled from galaxies. The Milky Way's descendant will slowly dim as aging stars exhaust their fuel and younger stars become rarer. The night sky will darken over geological timescales as the stellar population ages. Over far longer scales, tens to hundreds of trillions of years, the last stars will exhaust their fuel entirely, and galaxies will consist of stellar remnants, white dwarfs slowly cooling toward invisibility, neutron stars, and black holes. Eventually, gravitational interactions will scatter most of these remnants out of galaxies altogether, leaving isolated objects drifting through an expanding cosmos. Black holes will remain as the last major structural features. Through a quantum mechanical process described by Stephen Hawking, black holes slowly evaporate by radiating energy over incomprehensibly long timescales. A stellar mass black hole would take roughly 10 to the 67th power years to evaporate. Supermassive black holes would take far longer, but eventually even they would disappear. What remains is a diffuse, cold, expanding sea of particles and radiation. The voids that are a notable feature of today's universe will become everything. The filaments and clusters we see as the defining structures of the cosmic web are a transient phase. impressive on human timescales, but ephemeral in the context of cosmic time. The universe's long-term destiny, given what we understand about dark energy, is progressive emptiness. The void we inhabit, in this sense, is not just an anomaly of the present moment. It is a preview of the ultimate state of the cosmos. The KBC void is real. Its effects are measurable. But several key questions remain unresolved, and they sit at the frontier of current research. The most immediate is the exact depth and extent of the void. Measurements from different surveys and different teams have returned density deficits ranging from roughly 10% to 20%. The statistical significance of the void and how seriously it challenges standard cosmology depends heavily on which end of that range turns out to be correct. Better galaxy surveys with greater depth and sky coverage will pin these numbers down. Until then, arguments about the void's statistical rarity rest on somewhat uncertain ground. The causal connection between the void and the Hubble tension also remains under scrutiny. The void hypothesis predicts specific patterns in how the locally measured Hubble constant should vary with distance, decreasing as measurements extend to larger scales and exit the void's sphere of influence. Recent observations show hints of this trend, but the data are not yet decisive. More precise measurements of the expansion rate at different distance scales will test whether the void is the dominant explanation for the tension or merely a contributing factor. The question of whether the void challenges or violates the cosmological principle is also unresolved. Homogeneity is generally expected to hold at scales of several hundred megaparsecs and above. The KBC void spans roughly 600 megaparsecs, right at the boundary. Whether the principle is violated depends both on the precision of the void's measured properties and on theoretical questions about exactly what scale homogeneity is supposed to manifest at. Future surveys will extend three-dimensional galaxy maps to much larger scales, directly testing whether the universe is as smooth as the cosmological principle requires. The modified gravity question remains open as well. Testing whether gravity deviates from general relativity in void environments requires velocity field measurements with precision not yet achievable. The next generation of surveys will measure how galaxies move in and around voids with much greater accuracy. Any deviations from standard predictions would be a major discovery. The role of voids in studying dark energy is actively developing. Using void expansion rates and shapes to constrain dark energy is a relatively new observational technique, and it will mature rapidly as Euclid, Deci, and Vera Rubin deliver their data. Finally, there is the question of whether our cosmological understanding is biased by our location in ways we have not yet fully accounted for. We draw conclusions about the universe from measurements made inside a structure that is almost certainly affecting those measurements. Researchers are developing methods to model and subtract the void's influence from local data. But the modeling requires assumptions about the void's properties that are themselves uncertain. The deeper, more unsettling possibility is that our location inside the KBC void might be introducing biases we have not yet thought to look for. Every measurement of cosmic expansion, every inference about dark energy, every statistical analysis of large-scale structure made from within the void carries the imprint of our unusual position. Quantifying those imprints, distinguishing what we observe because it is universally true from what we observe because we happen to be standing inside a particular hole in the cosmos, is one of the central challenges of observational cosmology over the coming decade. In 2013, 3 astronomers mapping the universe's matter distribution found a 20% deficit in all directions, an enormous bubble of low-density space with us inside it. That observation, confirmed and refined by subsequent surveys, has grown into one of the most consequential findings in contemporary cosmology. The KBC void connects to the Hubble tension, one of the most actively debated problems in physics. It strains the cosmological principle, one of the foundational assumptions of modern science. It tests the standard cosmological model at its limits and motivates modifications to fundamental theories of gravity and inflation. It affects our measurements of the universe's expansion history and possibly its age. And it sits at the uncomfortable intersection of 2 unpleasant possibilities. Either we occupy an extraordinarily unusual location in the universe, a position that standard physics suggests should essentially never exist, or the standard physics is missing something important about how structures form on the largest scales. Neither conclusion is simple. Both are testable, and both represent genuine frontiers of scientific investigation. The next few years will be decisive. New telescopes are mapping the universe at unprecedented scales and resolution. The data they return will either confirm the void's extreme properties and force revisions to our models, or they will reveal that the void is less anomalous than it appears and that the standard framework is more robust than its critics suggest. Either way, the fact that we are living inside a measurably unusual region of the cosmos is not a minor detail. It shapes what we see, how we measure it, and what we conclude about the universe. The cosmos is under no obligation to be simple or typical, and our measurements of it are only as reliable as our understanding of the vantage point from which we observe. Understanding why the KBC Void matters requires appreciating how difficult it is to measure the three-dimensional structure of the universe in the first place. The challenge is fundamental. We observe the sky in 2 dimensions. Every galaxy appears as a point of light in a particular direction, but that position alone tells us nothing about how far away the galaxy actually is. 2 galaxies that appear adjacent in the sky might be separated by hundreds of millions of light-years in depth. For most of astronomical history, this limitation was essentially insurmountable. Photographs of the sky showed galaxy distributions in 2 dimensions, providing essentially no reliable depth information. The cosmic web, with its 3-dimensional structure of filaments and voids, was completely invisible. The breakthrough came with systematic redshift surveys. When light from a distant galaxy reaches us, its wavelengths have been stretched by the expansion of space during the journey. A galaxy farther away has had its light traveling through more expanding space, so it arrives with greater wavelength stretching, a larger redshift. By measuring how much a galaxy's light has been redshifted, astronomers can calculate how fast it is receding from us, and from that, roughly how far away it is. The first systematic redshift surveys in the 1970s and 80s were laborious. Each galaxy's spectrum had to be taken individually, requiring hours of telescope time per object. But even with small samples, the 3-dimensional structure that emerged was startling. Galaxies were not distributed randomly through space. They formed a web-like network, long chains and sheets surrounding enormous empty regions. The cosmic void structure became visible for the first time. The 1989 publication of the first CFA redshift survey revealed the Great Wall, a sheet of galaxies spanning 500 million light-years. At the time, the largest known structure in the universe. Its discovery forced a revision of theoretical expectations about how large structures could grow. Later surveys covered progressively larger volumes with larger galaxy samples. The 2-degree field galaxy redshift survey in the early 2000s mapped about 250,000 galaxies. The Sloan Digital Sky Survey, which began science operations in the year 2000, ultimately mapped the positions of over 1 million galaxies across a large fraction of the sky, producing the most detailed 3-dimensional map of the nearby universe ever assembled. The maps from these surveys show the cosmic web in stunning detail. Filaments twist and branch like the channels of a river delta. Voids appear as dark bubbles ranging from tens to hundreds of millions of light-years across, and rich galaxy clusters mark the intersections where multiple filaments converge. The Sloan Great Wall, identified in this data, stretches about 1.4 billion light-years, far larger than any structure previously known. The Hercules Corona Borealis Great Wall, identified in a survey of gamma-ray bursts rather than galaxies, may span as much as 10 billion light-years, though its status as a coherent physical structure remains debated. On the emptiness side, the Eridanus supervoid extends about 1.8 billion light-years, with a particularly severe density deficit, comparable to or exceeding the KBC Void in some measurements. These discoveries progressively revised upward our understanding of the scales on which structure exists. Each time a new largest known structure was announced, it pushed the limits of what standard cosmology could accommodate. The KBC Void fits into this pattern. It represents the largest identified underdense region in our vicinity, and its properties press at the boundaries of what the standard model predicts should exist. Measuring the KBC Void required a step beyond simple galaxy counting. The void is defined not just by a lower galaxy number density, but by a genuine deficit of matter. Verifying this requires accounting for survey completeness, observational biases, and the possibility that some galaxies are simply too faint to detect. Keenan, Barger, And Cowie addressed these concerns by using multiple independent surveys covering different areas of sky and comparing their counts to theoretical predictions for the expected galaxy density at different distances. The consistent result, a 20% deficit extending to approximately 1 billion light-years in all directions, was robust against these concerns. Subsequent studies using different methodologies have added independent confirmation. Analyses of the peculiar velocity field, the pattern of galaxy motions beyond what cosmic expansion predicts, show the signature expected from a large underdensity. Measurements of the kinematic Sunyaev-Zel'dovich effect, which traces the distribution of hot gas in galaxy clusters, show a deficit in our vicinity consistent with the void's extent. The convergence of independent lines of evidence strengthens the case that the KBC Void is a real physical structure rather than an artifact of any one survey's selection effects. The KBC Void is only one feature of the complex gravitational landscape that our galaxy navigates. Surrounding the void and influencing our motion through it are some of the most massive structures in the known universe. Understanding these structures helps illuminate why measuring anything from our location is so complicated. The most famous of these is the Great Attractor. For decades, astronomers noticed that galaxies across a wide region of the local universe, spanning hundreds of millions of light-years, were all moving in roughly the same direction toward a concentration of mass in the direction of the constellations Centaurus and Norma. This concentration, the Great Attractor, has a mass roughly equivalent to tens of thousands of Milky Ways. Our galaxy itself is moving toward it at around 600 kilometers per second, contributing significantly to our total peculiar velocity. For years, the Great Attractor was difficult to study directly. It lies in the so-called zone of avoidance, the band of sky obscured by the dust and stars of our own Milky Way's disk, which blocks observations of more distant objects. Only when X-ray and radio observations penetrated this obscuring veil did the true nature of the attractor become clear. It appears to be concentrated in a region containing the Norma cluster and associated filaments. But the Great Attractor is not actually the dominant gravitational influence on our motion at larger scales. Behind it, roughly 650 million light-years away, lies the Shapley Supercluster, the most massive concentration of matter within about 1 billion light-years. The Shapley Supercluster contains dozens of rich galaxy clusters, hundreds of thousands of galaxies, and has a combined mass of roughly 10 quadrillion solar masses. Its gravitational influence extends over hundreds of millions of light-years and significantly affects the bulk flows of matter throughout our region of the universe. The Milky Way is moving toward the Shapley Supercluster at a velocity component of roughly 200 to 300 kilometers per second. Adding to the effects of the local void outflow and the Great Attractor pull. These contributions partially cancel and partially add, producing our observed peculiar velocity relative to the cosmic microwave background. The Shapley Supercluster represents the kind of overdensity that the KBC Void conspicuously lacks. It is a concentration of matter so extreme that it rivals theoretical predictions for the densest structures that should form in our cosmological model. Its existence at the same time as the KBC Void, a vast underdensity on one side and a massive overdensity on the other, is part of what makes our region of the universe so dynamically interesting and statistically unusual. The Perseus-Pisces supercluster lies in roughly the opposite direction from Shapley, about 230 million light-years away. The Coma cluster, one of the most massive galaxy clusters in the nearby universe, lies about 320 million light-years away. These rich concentrations mark the filamentary wall surrounding the near side of the KBC Void. Mapping how these structures contribute to the local velocity field is crucial for separating the void's effect on Hubble constant measurements from the contributions of individual massive objects. This decomposition requires detailed modeling of the gravitational potential created by all of these structures simultaneously. The most complete models currently available account for masses out to about 300 million light-years and reproduce the bulk flows measured by galaxy surveys at the 70 to 80% level. The residuals, the fraction of observed motions that the models cannot yet explain, indicate that the true gravitational landscape is still not fully mapped. Extended surveys probing masses at greater distances, particularly the region between 300 million and 1 billion light-years, are expected to account for most of the remaining discrepancy. As this mapping improves, the contribution of the KBC void to our peculiar velocity will be better isolated and quantified, providing a more precise test of whether the void is large enough and deep enough to fully explain the Hubble tension. The KBC void leaves an imprint not just in galaxy surveys and velocity measurements, but in the oldest light in the universe, the cosmic microwave background. This imprint comes through a physical mechanism called the integrated Sachs-Wolf effect, and it provides a completely independent line of evidence for the void's existence. Light traveling through space gains and loses energy as it passes through variations in the gravitational potential. When a photon enters a gravitational well, a region of higher than average density, it falls in and gains energy. As it climbs back out, it loses that energy. In a static universe, these two effects would exactly cancel, and photons would emerge with the same energy they entered with. But in an expanding universe dominated by dark energy, the situation differs. While a photon is crossing a gravitational structure, the structure itself is changing. Dark energy causes the gravitational potential of overdense regions to decay over time as clusters effectively dilute relative to the expanding universe around them. A photon that enters a gravitational well and then climbs out as that well is becoming shallower gains more energy than it loses. The effect is small for individual structures, but cumulative over many. The inverse process applies in voids. A photon entering a void, a region of lower than average density and shallower gravitational potential, exits with slightly less energy than it entered with, because the void has deepened slightly during the transit. The potential well becomes more negative as the void expands and empties further. This leaves a cold imprint on the cosmic microwave background, along lines of sight that pass through voids. Astronomers have detected this effect by correlating cosmic microwave background temperature maps with galaxy surveys that identify void and cluster locations. Lines of sight passing through known galaxy clusters show slight temperature excesses. Lines of sight passing through known voids show slight temperature deficits. The correlation is statistically significant and consistent with a universe dominated by dark energy, which is required for gravitational potentials to decay during photon transit. This is an important test of the cosmological constant hypothesis. The integrated Sachs-Wolf effect only occurs in the dark energy-dominated regime. In a matter-dominated universe without dark energy, gravitational potentials would not decay, and the effect would vanish. Detecting the effect where it is expected, and with approximately the predicted magnitude, provides direct evidence that dark energy is causing the gravitational potential of structures to evolve. For the KBC void specifically, its enormous size means that its cold imprint on the cosmic microwave background is potentially measurable even without cross-correlation with galaxy surveys. Some researchers have examined the cosmic microwave background for a cold region corresponding to the void's location and size. Early analyses found marginal evidence for an extended cold region in the appropriate part of the sky, but the signal is difficult to isolate from the primordial temperature fluctuations present in the cosmic microwave background from the early universe. This connects to a separate and intriguing anomaly called the cold spot, a large, significantly colder than average region in the southern hemisphere of the cosmic microwave background sky, first identified by the WMAP satellite. The cold spot is about 0.1 degrees colder than the average and spans a region of sky roughly 10 degrees across. Various explanations have been proposed, including the possibility that it represents the imprint of a very large supervoid at low redshift. Studies have searched for a corresponding void in galaxy surveys at the location of the cold spot. Some have found evidence for an underdense region, while others have found the underdensity to be insufficient to fully explain the temperature deviation through the integrated Sachs-Wolf effect alone. The debate remains unresolved. What is clear is that large voids leave measurable imprints on the oldest light in the universe, providing a cosmological cross-check that bridges observations of the local matter distribution with measurements of the primordial radiation field. One of the most powerful tools in modern cosmology is also one of the most elegant, the use of Baryon acoustic oscillations as a cosmic ruler. Understanding how this technique works, and how the KBC void potentially complicates it, illuminates why our position in the universe matters so much for precision measurements. In the early universe, before atoms had formed, the cosmos was a hot, dense plasma of electrons, protons, and photons. Pressure waves, sound waves, propagated through this plasma, driven by the competing forces of radiation pressure pushing outward and gravity pulling inward. These oscillations set up standing waves with a characteristic scale determined by the speed of sound in the plasma and the age of the universe at a particular epoch. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, an event called recombination, occurring about 380,000 years after the Big Bang, photons decoupled from matter, and the pressure waves froze. The characteristic scale at which matter clustering was enhanced by these waves was imprinted into the distribution of matter. Today, more than 13 billion years after recombination, galaxies show a small but statistically detectable preference for being separated by approximately 500 million light-years, the acoustic scale set by those ancient sound waves. This preference appears as a subtle peak in the statistical clustering of galaxies. Because the acoustic scale is set by well-understood physics in the early universe and is calibrated against the cosmic microwave background, it serves as a standard ruler, a known physical length that can be used to measure cosmic distances and the expansion history. Baryon acoustic oscillation measurements have become one of the most reliable methods in cosmology, independent of the supernovae distance ladder and the peculiar velocity systematics introduced by the KBC Void. Surveys like BOSS, the Baryon Oscillation Spectroscopic Survey, and its successor eBOSS have measured the acoustic scale at multiple redshifts, mapping the expansion history of the universe across billions of years. The current Baryon acoustic oscillation measurements are consistent with the lower Hubble constant derived from the cosmic microwave background, around 67 kilometers per second per megaparsec, rather than the higher local value around 73. This is significant because Baryon acoustic oscillation measurements are largely immune to the peculiar velocity biases introduced by the void. The acoustic scale is measured at distances well outside the KBC Void's influence. This means that two independent large-scale measurements, the cosmic microwave background and Baryon acoustic oscillations, agree with each other and both point to the lower Hubble constant. Two local measurements, supernovae and Cepheid distances, agree with each other and both return the higher value. The divide is clean and sits precisely at the boundary of where the KBC Void's influence would be expected to operate. Local measurements within the void return an inflated value. Measurements probing beyond the void scale return the unbiased global value. This coherence is one of the strongest arguments for the void explanation of the Hubble tension. The divide is not random. It follows the expected spatial boundary of the void's gravitational influence. Future surveys like DESI, which will measure Baryon acoustic oscillations across a vastly larger survey volume than previous experiments, will sharpen this boundary test and constrain how much of the tension can be attributed to the void versus other possible explanations. Astronomers have developed increasingly sophisticated techniques for mapping the peculiar velocity field, the pattern of galaxy motions beyond what cosmic expansion accounts for. These maps have become one of the most direct diagnostics of the large-scale matter distribution, including the KBC Void itself. The principle behind peculiar velocity measurements is straightforward. If we know a galaxy's true distance independently of its redshift, we can compare that distance to the distance implied by its redshift, assuming pure Hubble flow. Any discrepancy indicates a peculiar velocity. The galaxy is moving faster or slower than expansion alone would produce, driven by local gravity. The challenge lies in measuring distances independently of redshift. Several methods exist, each with its own systematics and precision. The Tully-Fisher relation links the rotational velocity of a spiral galaxy to its intrinsic luminosity. Faster spinning spirals are intrinsically brighter. By measuring rotational velocity from spectroscopy and comparing the expected luminosity to the observed apparent brightness, astronomers calculate distance. The fundamental plane relation does the same for elliptical galaxies, using the correlation between size, luminosity, and internal velocity dispersion. Using these methods, researchers have mapped peculiar velocities for thousands of galaxies out to distances of several 100 million light-years. The resulting velocity field shows coherent flows, large-scale patterns where entire regions of space move together in the same direction. These flows trace the underlying matter distribution. Galaxies flow toward mass concentrations and away from underdensities. The maps produced from these surveys show exactly what the KBC Void hypothesis predicts. galaxies within the void are moving faster than Hubble flow would suggest, accelerated outward by the gravitational imbalance. The excess velocity is roughly consistent with the magnitude expected from a void of the KBC's size and depth. Galaxies approaching the void's edge from outside show the velocity reversal expected as matter falls toward the denser filaments surrounding the void. One major peculiar velocity survey, called the Cosmic Flows Program, has measured peculiar velocities for over 30,000 galaxies and constructed three-dimensional maps of the matter distribution derived from these velocities. These maps independently confirm the presence of a large underdensity in our vicinity. They also show the Laniakea supercluster's gravitational basin and the outflow from the local void. The quantitative agreement between peculiar velocity maps and the void density profile derived from galaxy counts is one of the most compelling pieces of evidence that the KBC Void is a physical reality. Two completely different observational approaches, counting galaxies and measuring galaxy motions, give consistent pictures of the same underlying structure. Improving peculiar velocity measurements is a priority for future surveys. The challenge is that current distance indicators have uncertainties of about 15% per galaxy, which means measuring the small systematic velocities introduced by the void requires large statistical samples. Future radio surveys using the 21-centimeter line of neutral hydrogen combined with improved calibration of distance indicators will reduce these uncertainties and extend peculiar velocity maps to greater depths. One of the more exotic possibilities for explaining the KBC Void's unexpectedly large size involves the properties of neutrinos, nearly massless fundamental particles that were produced in enormous numbers in the early universe and continue to stream through all of space today. Neutrinos have an unusual relationship with structure formation. Unlike cold dark matter particles, which move slowly enough to be gravitationally captured by overdense regions and help build structures from the bottom up, neutrinos move at relativistic speeds given their tiny masses. This means they can escape from small gravitational wells and stream over large distances without being captured. On scales smaller than their free streaming length, neutrino perturbations are washed out rather than amplified. The mass of neutrinos, though extremely small, is cosmologically significant because it determines that free streaming scale. Heavier neutrinos have shorter free streaming lengths and affect structure formation on smaller scales. Lighter neutrinos affect larger scales. In standard cosmology with very light neutrinos, structure formation proceeds efficiently at all scales above the neutrino free streaming length. In models with heavier neutrinos, still within observational bounds but toward the upper end, structure formation on intermediate scales would be suppressed. This suppression could alter the predicted distribution of voids and clusters in ways that might make supervoids, like the KBC Void, somewhat less improbable. Some hybrid models developed to address the challenges of modified Newtonian dynamics invoke neutrinos as a dark matter component. In these neutrino-hot dark matter models, massive neutrinos contribute a fraction of the overall dark matter density. The interplay between modified gravitational dynamics on large scales and the smoothing effect of neutrinos on intermediate scales can produce a matter-power spectrum that better matches observations than either standard cosmology or pure, modified gravity can achieve alone. These models remain speculative and contested. The cosmic microwave background is sensitive to the neutrino mass sum and places tight constraints on how much neutrinos can contribute to the dark matter budget. Current data favor very light neutrinos with minimal effect on structure formation, but the constraints are not yet tight enough to definitively rule out small neutrino contributions to the dark matter that might affect void statistics at the margins. Future measurements of the neutrino mass through laboratory experiments and cosmological observations will tighten these constraints significantly. The KBC Void, from one perspective, is simply a large region of space with fewer galaxies than average. That description, while technically accurate, misses almost everything important about it. From a cosmological standpoint, it is a testbed for our most fundamental assumptions. It strains the cosmological principle. It challenges the standard model's predictions for structure formation. It provides the most natural explanation for the Hubble tension, one of the most actively debated problems in modern physics. It offers the closest and most detailed laboratory for studying dark energy in a near-gravity-free environment. And it presents a case study in how our position in the universe shapes our perception of it. From a physical standpoint, the void illustrates the consequences of living inside a gravitational anomaly. Every expansion rate measurement made locally, every inference about cosmic age derived from local distance indicators, every model of dark energy constrained by nearby supernovae, all of these are conducted from within a region where the matter density is systematically below average, where the gravitational potential is shallower than typical, and where galaxies are moving outward at slightly elevated velocities. These effects are small individually, but collectively, they accumulate into measurable biases in our most precise cosmological measurements. From a philosophical standpoint, the void confronts us with a question that science has generally tried to move past. Are we in a special location? The cosmological principle embodies the assumption that we are not. The void creates friction with that assumption, not because we are special in any anthropocentric sense, but because we happen to occupy one of the statistically unusual regions of the universe, an extremely large underdensity whose very existence pushes the limits of what the standard model says should occur anywhere in the observable cosmos. Science operates by making measurements and constructing models that explain those measurements. When the vantage point from which measurements are made is itself unusual, those measurements carry systematic biases that can masquerade as fundamental physics. Recognizing this, characterizing it quantitatively, and correcting for it is the scientific response. The void is not something to fear or to find alarming in any human sense. It is an object of study, a structure of extraordinary scale that reveals the physics of dark energy, the statistics of large-scale structure formation, and the limitations of measuring an entire universe from a single unusual location within it. What makes the KBC Void genuinely compelling is that it sits at the intersection of multiple open questions simultaneously. Resolving it does not just answer one puzzle. It touches the Hubble Constant, the age of the universe, the cosmological principle, the nature of dark energy, the behavior of gravity on large scales, and the statistical predictions of inflationary models. Progress on understanding the void is progress on all of these fronts at once. The coming decade of astronomical surveys will deliver the data needed to resolve or sharpen each of these questions. Billions of new galaxy positions, millions of new spectra, thousands of new void maps at different cosmic epochs. This flood of information will force either confirmation of the void's anomalous nature or reveal that current measurements have understated its size and depth relative to what a more complete sky survey would show. Either outcome leaves us with a clearer picture. Either the universe is stranger and less uniform than we assumed, with supervoids as large as the KBC occurring at rates that challenge our models, or our local neighborhood is genuinely a statistical outlier, and we must accept the discomfort of occupying an unusual cosmic address while still working out what implications that has for everything we think we know. The universe does not owe us a typical location. It does not owe our measurements a clean, unbiased signal. What science can do is identify the biases, quantify them, account for them, and reach understanding that is valid regardless of where the observer happens to stand. That is the work currently underway, and the KBC Void, 2 billion light-years of cosmic emptiness surrounding our galaxy, is both the reason the work is necessary and the subject it is most urgently needed to explain. To fully appreciate the void, it helps to think concretely about what being inside it actually means for the observable universe as seen from Earth. When astronomers look outward from our galaxy, they do not see a uniform distribution of other galaxies. They see a structured landscape, clusters and filaments in some directions, relative emptiness in others. The cosmic web is real and visually apparent in galaxy surveys, once you have the depth to map it properly. From inside the KBC Void, a specific pattern emerges that reflects our position. In every direction, at distances of roughly 500 million to 1.5 billion light-years, there is a shell of relatively higher galaxy density. This is the wall of the void, the filamentary structure that marks the transition between the void's interior and the denser regions of the universe beyond. Surveys at these distances show a concentration of galaxy clusters and superclusters. The Perseus-Pisces supercluster to one side, the Shapley supercluster in another direction, the Horologium Reticulum supercluster toward the south. These massive concentrations form a roughly spherical shell around us, a consequence of sitting inside the void. This observational signature was actually noticed before the void was formally identified. Astronomers studying the distribution of galaxy clusters at different distances found a statistical excess of clusters at redshifts corresponding to the void's outer boundary. At the time, this excess was attributed to various causes. The void explanation unifies these observations. We see the shell because we are inside it. The interior of the void, between us and that outer shell, is not empty in the everyday sense. Light years of space are not distinguished by their content to any observer who cannot see individual atoms. The void contains dark matter, dark energy, occasional dwarf galaxies, intergalactic gas filaments, and the same physics that governs all space. What is absent is the rich concentration of large galaxies, clusters, and filaments that make up most of the mass in typical filamentary regions. If you could somehow freeze cosmic expansion and travel outward from the Milky Way at the speed of light, here is roughly what you would encounter. For the first 60 million light years, you would pass through the local group and the nearby galaxies of the Virgo cluster region, a familiar, moderately populated environment. Between 60 and 200 million light years, galaxy density drops off from the Virgo cluster's influence, and you enter the more sparsely populated inner void. From 200 million to 500 million light years, you traverse the heart of the underdense region, passing occasional galaxy groups scattered through relative emptiness, with the matter density roughly 20% below the cosmic mean. Beyond 500 million light years, you begin encountering the richer filamentary walls, and by 1 billion light years, you have reached the outer boundary of the void structure and entered more typical cosmic density. That journey, from familiar local neighborhood through a billion light years of relative emptiness to the void's outer wall, is the scale of the structure we inhabit. For comparison, the distance from our galaxy to Andromeda is about 2.5 million light years. The void extends about 400 times farther than that in every direction. This scale makes the void essentially permanent on any timescale relevant to human civilization or even the history of life on Earth. The Milky Way is moving outward within the void, but it would take hundreds of millions of years to travel from one side of the void to the other at our peculiar velocity. And meanwhile, the void itself continues expanding due to dark energy, growing faster than our galaxy can move through it. We entered this void billions of years ago, and we will not leave it on any timescale that has meaning for human existence. Mapping the KBC Void and resolving the questions it raises depends on building progressively more complete and precise three-dimensional maps of the galaxy distribution in our region of the universe. This is an observational challenge of considerable scale, and one that multiple current and future surveys are specifically designed to address. The fundamental bottleneck has historically been spectroscopic follow-up. Identifying millions of galaxies in photometric images is relatively straightforward. Digital sky surveys can catalog billions of objects from images alone. Converting that catalog into a three-dimensional map, however, requires measuring the redshift of each galaxy, which means taking a spectrum that shows how much the galaxy's light has been stretched by cosmic expansion. Spectroscopy takes far more telescope time than imaging. For every galaxy image that can be captured in a short exposure, getting a usable spectrum might require minutes to hours of dedicated time on a large instrument. Multi-object spectrographs, instruments that can measure spectra for hundreds or thousands of galaxies simultaneously by routing their light through optical fibers to a spectrograph, have dramatically increased the efficiency of redshift surveys. The Sloan Digital Sky Survey pioneered this approach, placing 640 optical fibers on a large focal plane and taking spectra of hundreds of galaxies at once. Its successors have pushed further. The DESI instrument on the Mayall telescope in Arizona positions 5,000 robotic fiber positioners simultaneously, capturing 5,000 spectra in a single exposure. Over its 5-year baseline survey, DESI expects to collect spectra for approximately 40 million galaxies and quasars, mapping the universe's large-scale structure from the local universe out to redshifts above 3.5, corresponding to distances when the universe was less than 2 billion years old. For the KBC Void specifically, what matters most is completeness at relatively low redshift, the region from roughly 50 million to 1.5 billion light years. Current surveys have reasonable but not complete coverage of this range. Deeper surveys that detect fainter galaxies will improve the completeness of the galaxy census within the void, reducing the uncertainty in how deep the density deficit actually is. The foremost instrument on the VISTA telescope and the Laniakea spectroscopic explorer being planned for a future large telescope will extend spectroscopic coverage to fainter objects across large sky areas. The Subaru Prime Focus spectrograph will provide deep spectroscopic surveys over wide fields. Each of these instruments adds coverage that will improve the characterization of the KBC Void and the broader cosmic web in our neighborhood. Photometric redshifts, estimates of galaxy distance based on their colors rather than their spectra, offer a complementary approach. While less precise than spectroscopic redshifts, they can be measured for many more galaxies in the same telescope time. The Vera Rubin Observatory will generate photometric redshifts for approximately 20 billion galaxies over its decade of operation. For statistical studies of large-scale structure, measuring the power spectrum of galaxy clustering, identifying voids in three-dimensional space, measuring the shapes and sizes of the void population, photometric redshifts from surveys of this scale provide extraordinary statistical power despite their individual imprecision. Euclid combines both approaches. It will take spectra for about 35 million galaxies at high redshift and produce high-quality photometric redshifts for several billion more. Its primary science goals, measuring dark energy and modified gravity through weak gravitational lensing and galaxy clustering, will simultaneously produce a comprehensive map of the large-scale structure around us and at higher redshifts, providing the context needed to understand how typical or atypical our void environment is. The cumulative effect of these surveys over the next decade will be a revolution in our knowledge of the three-dimensional matter distribution across the observable universe. The specific questions about the KBC Void, its exact density profile, its true statistical rarity, its contribution to the Hubble Tension, will all be addressed with data far superior to what currently exists. Among the multiple independent lines of evidence for the KBC Void, one of the most physically distinct is provided by the thermal Sunyaev-Zel'dovich effect, a mechanism by which clusters of galaxies leave imprints on the cosmic microwave background. The cosmic microwave background fills all of space uniformly at a temperature of about 2.725 Kelvin. As photons from this ancient radiation field travel through the universe, they can interact with electrons in the hot gas that fills galaxy clusters, the intracluster medium. When a low-energy photon scatters off a hot electron, it gains energy and is shifted to slightly higher frequency. This removes photons from the low-frequency part of the spectrum in the direction of a cluster and adds photons at higher frequencies. The result is a characteristic spectral distortion that appears as a temperature decrement in cosmic microwave background temperature maps at frequencies below about 217 GHz and a temperature increment at higher frequencies. This distortion, predicted by Rashid Sunyaev and Sunyaev-Zel'dovich in 1969, is proportional to the integrated thermal pressure of the cluster's hot gas along the line of sight. It is a direct tracer of the hot baryonic content of galaxy clusters, the gas that has been shock-heated to tens of millions of Kelvin by the cluster's gravitational potential. Cosmic microwave background surveys, like the Atacama Cosmology Telescope and the South Pole Telescope, have used this effect to detect and catalog thousands of galaxy clusters across the sky. The Planck satellite's All-Sky survey produced a catalog of roughly 2,000 confirmed Sunyaev-Zel'dovich clusters. These catalogs are largely independent of optical galaxy surveys because they trace the cluster gas rather than the stars. When the distribution of detected clusters is examined in the volume corresponding to the KBC Void, a density deficit is found that is consistent with the galaxy count measurements. Fewer clusters means less hot gas, means a smaller signal per unit volume. This independent confirmation is valuable, precisely because it relies on completely different physics. Galaxy counts trace the stellar component of matter, visible stars and galaxies. The Sunyaev-Zel'dovich effect traces the hot gas in clusters, a distinct component of the baryonic matter that is particularly concentrated in the most massive objects. The fact that both tracers show the same deficit strengthens the case that the void represents a genuine shortfall of all matter, not just an artifact of how galaxy formation happened to proceed in this region. Future cosmic microwave background surveys with higher sensitivity and resolution, including CMB Stage 4 and the Simons Observatory, will detect Sunyaev-Zel'dovich clusters down to lower masses and at greater distances, substantially improving catalog completeness within the void volume. An entirely new observational window on the universe's expansion rate has opened in recent years: gravitational wave astronomy. Since the LIGO detectors first detected gravitational waves from a merging pair of black holes in 2015, and especially since the 2017 detection of a neutron-star merger accompanied by a gamma-ray burst and optical counterpart, gravitational wave observations have offered a new method for measuring the Hubble constant. Neutron-star mergers and potentially black hole and neutron-star mergers are what physicists call standard sirens. Like Type 1, a supernovae serving as standard candles, neutron-star mergers can be used as distance indicators. The amplitude of the gravitational wave signal depends on the intrinsic properties of the merger and on the distance to the source. By analyzing the gravitational waveform, physicists can extract the distance to the merger without any electromagnetic observations. If that distance is combined with a measurement of the host galaxy's redshift, the Hubble constant can be calculated directly. The first such measurement, from the neutron-star merger known as GW170817, returned a Hubble constant of approximately 70 kilometers per second per megaparsec, right between the early universe estimate of 67 and the local latter estimate of 73, with an uncertainty of about 14%. As more events accumulate, the uncertainty will decrease, and gravitational wave cosmology will independently determine which end of the tension range is more correct. Crucially, gravitational wave sources are at specific distances, and their placement relative to the KBC Void matters. The original neutron-star merger occurred in a galaxy about 130 million light-years away, squarely within the KBC Void. If the void is inflating local distance measurements, the gravitational wave measurement would also be affected, though in a different way than the supernova distance ladder. Comparing the gravitational wave result with predictions from both the early universe model and the void-corrected local model will provide a new diagnostic. As detectors improve, the ongoing upgrades to LIGO and Virgo and the upcoming LIGO India detector, the event rate will increase to dozens or hundreds of detections per year. With a large sample of events at various distances, the dependence of the apparent Hubble constant on distance will be measurable. The prediction from the void hypothesis is that events within the void should return a systematically higher Hubble constant than events at distances beyond the void's edge. This prediction is directly testable once enough events have been detected across the full range of relevant distances. The future Einstein telescope in Europe and the Cosmic Explorer in the United States will be enormously more sensitive than current detectors, detecting neutron-star mergers out to distances of many billions of light-years. These instruments will produce catalogs of thousands of standard sirens, spanning both the interior of the KBC Void and the more typical density regions beyond it. The resulting Hubble constant measurements as a function of distance will provide one of the most direct tests of whether the void is responsible for the local Hubble tension or whether some other explanation is needed. Science rarely arrives at clean conclusions. More often, discoveries open onto further questions, and the apparent resolution of one problem reveals three more lurking underneath. The KBC Void is a perfect example of this process. A straightforward observation, counting galaxies within a billion light-years and finding 20% fewer than expected, cascades into questions about the expansion rate of the universe, the age of the cosmos, the nature of dark energy, the validity of the cosmological principle, the behavior of gravity on large scales, and the reliability of every precision measurement in modern cosmology. Each of these questions is individually significant. The void connects them into a single, coherent puzzle. The resolutions, when it comes, will likely not be dramatic. Science rarely announces itself with clean breaks. More likely, new surveys will gradually refine the void's density profile. The Hubble tension will be pinned down with higher precision at multiple distance scales. The velocity field within and around the void will be mapped with new clarity, and models will be adjusted to accommodate the accumulated evidence. The adjustment may be minor. Perhaps standard cosmology underestimates the frequency of large voids by a factor of 2 or 3 without requiring new physics. Or it may be significant. Perhaps the void requires modified gravity or altered inflationary physics, demanding a genuine revision of the theoretical framework. In either case, the universe will remain strange, and the work will continue. The KBC Void is not an anomaly in the dismissive sense of something that can be wished away. It is a feature of the cosmos, A real, measurable, enormous region of below-average density that surrounds our galaxy in every direction and extends for 1 billion light-years. Its reality is not in question. Its full implications are. We live in a remarkable time for cosmology. The instruments coming online in this decade are genuinely capable of answering questions that have been unresolvable for the past generation of astronomers. The data that Euclid, DESI, Vera Rubin, and their companion experiments will return over the next 10 years will be transformative. The maps they produce will settle the statistical question of the void's rarity. The expansion rate measurements will resolve or deepen the Hubble tension. The dark energy constraints will narrow the range of possible physical explanations. Our galaxy is inside a bubble of space 2 billion light-years across where matter is measurably scarce. We know this with confidence. What we do not yet know is what that tells us about the universe beyond the bubble, whether the standard framework describes that universe correctly, whether gravity and dark energy behave as we expect on scales we cannot yet map precisely, and whether our current measurements are telling us something about the cosmos as a whole or something about the unusual corner of it we happen to inhabit. Those are the open questions. They will be answered. The void, for all its emptiness, turns out to be one of the most information-rich environments in the observable universe, not despite its emptiness, but because of it.